In this section, we're going to take a look at the idea of lines and planes in the three-dimensional Cartesian plane. We're going to start with lines. They're a little bit easier to work with in 3 dimensions. So let's say we have a line L. It's in space, and it's parallel to a vector v. All right. So if we know some sort of vector v that's parallel to the line, and there's a point that's on that line, let's call that x1, y1, z1. Those values A, B, and C are known as the direction numbers because those are the A, B, and C coordinates, or X, Y, and Z coordinates, excuse me, to which they're going to be parallel to that line. The vector is called the direction vector, and from there we can generate 2 different types of equations. One of which, the more useful type that I found, is the parametric equations. And parametric equations are exactly what they sound like. They're built on a parameter t, and it gives us all the points on a line as you vary the value t. And so what you do is you take the direction numbers, you take the point on the line, and you just throw a t in front of the direction numbers, and that gives you 3 separate equations for the lines. And so another way to try to build that is a relationship between x, y, and z, a, b, and c, and x1, y1, z1. You can eliminate the parameter essentially and solve for t in all 3 of those. So another way to write this is to say that t is going to be equal to x minus x1 over a equals y minus y1 over b, z minus z1 over c, as they're all equal to one another. Again, parametric equations are going to be the ones that are more useful. However, these symmetric equations, I've seen those before, although not too useful. So let's take a look at several examples to where we can build the equations of lines in space. All right, and the first one's a really easy one. So we're passing through a point 2, 0, negative 3, and we're parallel to a vector 2, 4, negative 2. All right, so clearly, since we have a point, that's going to be our x1, y1, z1, and the direction numbers are the coefficients of I, j, k in our vector v. And so if we want the parametric equations, we're going to say that x is going to be equal to 2 plus 2t, right? And again, x1 is 2, a is 2 as well. For y, that's going to be 0 plus 4t, otherwise known as 4t. And then finally, z is going to be equal to negative 3 minus 2t. We should note that the domain for the parameter t is all real numbers. All right, so we want to make sure that we define that t is a parameter and that it is indeed all real numbers for us, because that way we know that a line is going to move infinitesimally through space and t can assume any number in that domain. The symmetric equations, we could just solve each of x, y, and z for t and get the symmetric equations. All right, so we're going to say that x minus 2 over 2, right? Or we could just use the formula. I just literally looked at the first equation and solved it for t. Is going to be equal to y over 4 is going to be equal to z plus 3 over negative 2. And all of those are equal to our variable t, although it's not as useful. Right, so that's going to be our parametric and symmetric equations, not meant to be too difficult. A second example. A problem that you might have faced in pre-calculus very often is given 2 points, try to find the equation of a line through 2 points in 2 dimensions. Now we're going to look at that same equation in 3 dimensions. First of all, we have a point, and it doesn't matter which one we use for x1, y1, z1. I'm just going to use the second one because it contains a 0, and usually zeros make things a little bit easier. We need to find a direction vector. And that's going to be really easy because all we're going to have to do is take the initial minus terminal and we can get a vector out of that. So let's call the first vector P, the second vector Q, and let's find a vector PQ to represent our A, B, and C. So that's going to be negative 3 minus 7 is negative 10, 0 minus a minus 2 is 2, 6 minus 6 is 0. And that's going to define our A, B, and C for this problem. Finally, we can generate the symmetric equations as well as the parametric equations nicely. So let's start with parametric. X is going to be equal to x1, which is -3, plus at, a is -10t. Y is going to be equal to 0, and then b is 2, so that's going to be plus 2t, otherwise known as 2t. And then finally for z, we know that z1 is 6, we know that c is 0, and so z is just a constant, okay? So no matter what, z is always going to be 6. Again, we should define that t is any real number because the line moves infinitesimally. The symmetric equations, unfortunately, do not exist for this equation, or at least for this line. And I'll illustrate why, because if you'll notice, if we were to solve each of these parametric equations that we just got, notice that one of them we're going to be dividing by 0 to be able to solve. All right, but let's just go through and solve it. So our t is going to be equal to x plus 3 over -10 if we solve for t in the first, which is going to be equal to y over 2 in the second, and that one's easy. And then finally, for the third one, we get z minus 6 over 0, which means that the symmetric equations do not exist. All right, so for this one, we're only worried about the parametric equations. Finally, a third example. Let's find the equation of the line that passes through -3, 5, 4. It's not parallel to a vector, it's parallel to a line. And the line is 3, -2, and x minus 1 over 3, y plus 1 over -2, and then z minus 3. Right? So we already know a point, x1, y1, z1. All right, so that's easy. We just need some direction numbers. The good news is the direction numbers are parallel to the line in the denominator of the symmetric equations. Right? So in this case, A is 3, B is -2, C is 1. And we can very easily build both the parametric and symmetric equations given this information. So x is going to be equal to -3 plus 3t. Y is going to be equal to 5 minus 2t. Z is going to be equal to 4 plus t. T is an element of the real numbers. Also, we need the symmetric equations, which means we need to solve each of the above for t, set them equal to each other. So the first one, x plus 3 over 3. Second one, y minus 5 over -2. Third, z minus 4 over 1, or just z minus 4. Right. So as we see, building the equations of lines in space is actually fairly easy. Now in the next section, what we're going to be doing is looking at how we can extend this to being able to build the equations of planes in space. And usually that's a little bit more useful, although not necessarily any more difficult.